Okay, this is 4.1, number 31. We're finding absolute extrema, and this one's weird for factoring, so we need to talk about this too. To find absolute extrema, you find the critical numbers, and you test the critical numbers and the endpoints in the original function to find the y values. So for finding the critical numbers, we'll have y prime equals 3 going along for the ride. Bring the exponent forward 2/3, rewrite the base, take 1 off the exponent, negative 1/3, minus 2. And our 3's cancel, so that works out kind of nice. And we want to recognize that there is a negative exponent, so there's a denominator, but you don't want to have separate fractions. You need to have one whole fraction. So one way that you can do this is, well, I guess there's a couple ways you could do it, but you could, let me just play with this for a minute. I think I'm going to do it an easier way. Y prime equals 2 over x to the 1/3 minus 2. And it might just be easiest if we multiply the second one by x to the 1/3 over x to the 1/3 rather than factoring, which is what I was planning on doing. And that's going to give us 2 minus 2x to the 1/3 over x to the 1/3, and that works out beautifully. Okay, so now we're going to factor out a 2, which doesn't do much. Y prime equals 2 times 1 minus x to the 1/3 over x to the 1/3. And we're going to find our critical numbers. And remember, critical numbers are where the values where they exist in the original function, but they either don't exist in the derivative or they cause the first derivative to be 0. So to find out where the first derivative is 0, you set the numerator of the first derivative equal to 0, because when the numerator of a fraction is 0, the whole fraction's worth 0. So then we have 2 times 1 minus x to the 1/3 equals 0. And you can divide by 2 on both sides, and then you can just have 1 minus x to the 1/3 equals 0. Add x to the 1/3 to both sides. Yeah. And then next you could cube root both sides. So raise it to the 3rd power, and you can already see what the answer is, but sometimes you can't. So we get 1 is equal to x, and that's a critical number because it causes the numerator of the first derivative to be 0, so the whole derivative would be worth 0. The other one, we set the denominator of the first derivative equal to 0, because that's where the first derivative does not exist because it zeroes out the denominator. So then we have x to the 1/3 equals 0, or x equals 0, and that's another critical number. So we have x equals 1 is a critical number, and x equals 0 is a critical number. And we test those in the function. So when we put x equals 0 into the original function, you're going to have 0, 0. So you're testing your critical number. And in this case, we have 2 of them. And now I'll put 1 into the function to find the corresponding y value. And when I do that, I get 1. 1 is also an endpoint, by the way. We have to test both the endpoints. We already did 1, so now we'll do negative 1. EP's for endpoint. And when I plug negative 1 into my function, I'm going to come back with a value of 5. So now the only thing is to draw the conclusion. Our lowest y value is going to be our absolute min. Our highest y value is going to be our absolute max. Remember, absolute extrema happen either where you have critical numbers or at the endpoints of an interval. So for absolute extrema, you have to be given an interval. So our lowest y value is here. So that means that we have an absolute min at the x part of the coordinate, 0. And our highest y is here. So we have an absolute max at the x part of the coordinate. X equals -1. All right, so that is that one. It just wasn't too bad, actually. It turned out a little bit better than if we would have factored it, but we're still going to have to do some weird factoring coming up, so we'll get there.